We're going to start chapter 4 today, which is all about the atom. When we're talking about atoms, we have to get used to using their chemical symbols and using the periodic table to figure out information about them. So every element has a chemical symbol, and it could be one letter, it could be two. For example, nickel is capital N with a lowercase I. When you have two letters, the first is always capitalized and the second is always lowercase. All right, so we're not going to see N capital I. You are always going to see N with a lowercase I. Now, you also may see just a single letter. N is nitrogen, okay? Now, when we're writing formulas or looking at formulas, there's a lot of pieces of information in here. So when you look at SO3, you see S, which you will start to recognize sulfur, and with no subscript under here, so a subscript is the number that's below. When you don't see anything, it's an assumed 1. Okay, and then we see oxygen and we see 3 oxygen. So that 3 just represents how many O's and the 1 represents how many S's. Okay, so we would say SO3. We typically do not write S1O3. So chemical formulas are basically a way of presenting information about the chemical proportions. So for this one, C has 6 components to it. H has 12 and O has 6. So that means one molecule of this contains all of these, okay? They don't split up. And so these will always have a certain ratio of numbers to elements. And we're going to learn how to write those as we go through this semester. Now, we're going to look at a little bit of the history of the atom, just so you can kind of understand where we started and where we're at right now. And one of the biggest things we are going to talk about is John Dalton's atomic theory, and this was in 1808, and he had some postulates, which we're going to look at. You will not have to memorize these. You may just have to recognize them, but you will not have to memorize them or ever completely write them out. So his theory was an element is made of particles called atoms, and we know that to be true. Atoms of the same element are identical. We are going to learn that this has been disproven. We can see that the number of neutrons and the number of electrons do change. So this was revolutionary at the time. Some of it still holds true, some of it doesn't. Atoms cannot be divided. This also was found not to be true because atoms can be divided into protons, neutrons, and electrons. Okay, but for it to be actually the element, you can't break it down any further. So a little bit true, a little bit untrue. All right, compounds are created when atoms of different elements are bonded together. We call this the law of constant composition and the law of multiple proportions. So just because we have nitrogens and oxygens together doesn't mean that it's always the same thing. So we could have an NO, nitrogen dioxide, nitrogen monoxide, NO2, nitrogen dioxide, or N2O, dinitrogen oxide. So there are many different ways that the elements and they can combine to create ratios of compounds. And each of these has different properties as well. Number 5, atoms are not created or destroyed in a chemical reaction. A chemical reaction simply changes the way the atoms are grouped. This is still true today. Okay, nothing comes from the atmosphere. Everything we have is already in our atmosphere. Okay, we're just rearranging. And then this is how Dalton imagined the atom to look. He did not think that it had anything inside of it, and we do know today that it did. But this was at least a good start of what kind of was going on and what it appeared to be. So an example here that we're going to look at is if you had 14 carbons, you had 9 hydrogens, and 5 chlorines, how would you write that? So again, we call these subscripts. We do not write the number in front. Okay, we're going to talk about what in front means later on. We write it below, so you're not going to be writing C14. It is C with a little 14, H with a little 9, and Cl with a small 5. Okay, so just some making sure that you are doing it the correct way as we continue on through this year. So again, this is what John Dalton believed our atom to look like in about 1803, 1808. And then we're going to start to see how we progressed. This is more what we believe the atom to look like today. We're not really going to talk about Schrodinger's model of the atom, but I just like you to see how we figured out there are things inside and then where they're located. And then this was a model for quite a while. People still believe that a lot, but we are getting into understanding this model. So here we go, J.J. Thomson here. We are looking at his experiment and how we added to our knowledge of the atom from John Dalton's idea. So J.J. Thomson, his experiment was called the cathode ray tube, and you will have to know that title. The cathode ray tube, and you will have to know J.J. Thomson. And he determined the charge to mass ratio. So what the heck does that even mean? That means that he shone a laser through, and what he thought was that it would go continuously straight. What happened is it actually curved up towards this positive magnet, and because it was attracted to the positive and not the negative, he realized that electrons are negative, because in our world and in chemistry, the idea that positive and negatives attract is such a fundamental idea to describe a lot of things. So basically, the cathode ray tube by J.J. Thomson helped us discover the electron in the atom and that it had a negative charge. So again, knowing the name of the experiment, the scientist, what it discovered, okay, is what's important here. You will not have to draw a picture of what's going on here. Now, from this idea, so again, remember John Dalton, his idea of the atom was just a filled-in sphere. And now we have added to it due to J.J. Thomson's discovery, and what he created was found here, and we call it the plum pudding model. Plum pudding was a delicacy at that time, and his idea was instead that the pudding portion here was positive, and that there were negative electrons, which he called the plums, floating around inside. So his idea, this positive and negative, was that the atom was neutral, which we know that to be true today. So he was describing how there had to be positives if there were negatives, because he did know the atom was neutral. So we call this the plum pudding model. And again, we had negative plums inside a positive sphere. And we're getting closer to what our atom looks like, but we do know that to be not true today. Then comes along J.J. Thomson's co-worker, Ernest Rutherford, a little bit later, and he discovered the components of the nucleus. So let me just give you a quick description of what happened here. He actually shot alpha particles, which are positive particles, onto a thin gold sheet. And what he anticipated happening was he assumed they would all just go through. Okay, but instead, most of them went through, and some were actually kind of scattered opposite directions. And that is where the discovery of the nucleus was created, or was, figured out. So if the plum pudding was correct, they would have gone all the way through. Instead, some were deflected back, and every time they were deflected back, we now know that they were probably hitting the nucleus. Okay, which we know to be in the center. So most of them went straight through. The ones and the few that hit the nucleus, either straight on or to the side, were deflected. So we actually figured out that the plum pudding model was disproved, and therefore we then discovered the nucleus in the center. Nucleus in the center of the atom. So again, you do have to know the scientist names, the experiment name, which is the gold foil experiment, and then also what he discovered, which was that there is a nucleus in the center of the atom. Now we're going to fast forward, obviously, to what we still think of as the atom today. We know that we have a center nucleus, and that nucleus is made up of two components. The nucleus is made up of protons and neutrons. Protons have a positive charge, P and P, help you remember that. They are found in the nucleus, and we're going to talk about how they affect the atomic number a little bit later on. And then the other component in the nucleus is neutrons. Neutrons are neutral. They have no charge. We find them in the nucleus, and they are about the same mass as a proton, okay? So this is a very heavy center of the atom. And then we have around the atom electrons, and they are found outside the nucleus. They are negatively charged, and in a neutral atom, we'll talk about what that means, they are equal to the number of protons. Okay, so nucleus made up of protons and neutrons. Around in the shells are the electrons. So again, the nucleus, although we portray it as being similar size to different components in the atom, the nucleus is very, very, very small compared to the overall atom. I always like to show my students that if you were to have a circle, it would truly just be the smallest dot. That would be the nucleus comparatively in size, okay? We call all this extra space the electron cloud, and that is most of the volume in the atom. Now, although this is small, it is very dense, and it actually accounts for most of the atom's mass. Protons and neutrons are a lot heavier compared to electrons. So although it's small, it has most of the mass. Most of the volume is around the nucleus in what we call the electron cloud. Okay? Now we're going to start looking at notation of atoms so that we can understand how protons, neutrons, and electrons are calculated. So every element on our periodic table has an atomic number, and a lot of times we use Z for atomic number. That is because A is taken here, you will see. And when we write a symbol, we always, or an elemental symbol, we have the element symbol here. And then on the bottom is our atomic number, and I will tell you in a few slides how we're going to use that. And then at the top of the symbol is the mass number, and the mass number is made up of the protons and neutrons added together. So, for example, if we have carbon right here, this is our mass number. It's always at the top, and this is our atomic number. So we will always see this written in what we call atomic notation, and we will be utilizing that. Now, I did discuss this a little bit, but remember the proton and the neutron are very similar in size, and you can see the electron being very, very small. So this is just kind of a nice overall where it's located, the charge of it, and then the size comparisons. Now, you are going to see electrons written as E- often, protons as P+, and neutrons as N with a 0, so please make sure you are comfortable using that. Now, how do we find the number of protons, neutrons, and electrons in an atom? Now, I want to preface that this is going to be a neutral atom. We will not be using neutral atoms all the time. So the term neutral obviously means there is no overall net charge. So therefore, in a neutral atom, protons and electrons are going to be the same value. So to find the number of protons, it is the same as the atomic number. And remember, I told you, if you are given an atomic symbol, the atomic number is the 1 on the bottom, okay? So the same as the atomic number. I'm going to skip to electrons. They are the same as the number of protons. And I am going to continuously warn you that this is for neutral atoms. We will learn it to be different as we go through here. But if it is neutral, they are the same. That means the negative charges cancel out with the positives. Therefore, we can consider it neutral. And then neutrons is a little bit different. You are going to take your mass number, which we know to be provided on our symbol or on the periodic table, and we are going to subtract the number of protons or the atomic number, either one, whichever one you're comfortable with, because they are the same. Now, protons will never change, okay? It doesn't matter what form of carbon or aluminum or sodium we have, the protons never change, okay? They are the identity of the atom. Now, neutrons, we're going to learn, will change. Electrons will change, but protons don't. This is the identity of the atom. If you have the number of protons, you have the atomic number, you know what the atom is, okay? So let's go ahead and practice. We have Si, which we're going to learn is silicon, and then we go ahead and have The atomic number, so I want to remind you the atomic number is the bottom, so that is going to be a 14. The mass number is provided on the top, that is a 29. Okay, and then we're going to go ahead and do our protons. That is the same as the atomic number, so that is 14. Now, I've been telling you if it's neutral, protons and electrons are the same. This is neutral. Let me show you what not neutral would look like just so you're comfortable. It would have some sort of charge up in the corner. We do not see that, so we know that the protons and the electrons are the same. Now, to find the neutrons, we're going to subtract the mass minus the atomic number or the number of protons. So that's a pretty easy subtraction here, and we get 15. Okay? Make that a little weird here. All right, so let's do this for another one. This is a symbol on the periodic table. A couple things to note here. The one that is a whole number, it is written in a million different places depending what periodic table you're using. The whole number is always the atomic number. The number with the decimals is always going to be the mass number, and you will round that when you're going to use it. This is the symbol, and this is typically the name. You will have a periodic table, on every single test and everything. So make sure you're getting comfortable finding those. So for bismuth, the number of protons is going to be the atomic number 83. We don't have anything telling us different that this is an ion, so we're going to go ahead and write the electrons as 83. And then our neutrons, I told you we're going to round it. So remember, when you round to a whole number, you have to look what's next to it. This is a 9, so therefore this would increase this to 209 instead of 208. You do not just cut it. You look at the next number. If it's 5 and above, you round it up. If it's 4 and below, you keep it what it is. So mass number minus atomic number or number of protons gets you 209 minus 83. You will always have a calculator in this course as well, so do not worry. It is 126. Okay? So that is for neutral atoms. Let's continue on for isotopes. What is an isotope? An isotope is an atom, okay, but it's a specific form of an atom, and it's going to be an element that has a different number of neutrons. So remember, I told you, protons never change, never. But I told you neutrons can. When the number of neutrons is different than the periodic table, okay, we call that an isotope. And isotopes are very common. You use isotopes of carbon for radioactive dating, to determine how old fossils are and things like that. So isotopes are very common in our world, and they're used for a lot of different things. So again, they have a different number of neutrons. Now, when we are affecting the number of neutrons, we are also affecting the mass, which is actually more what is affected. So when we affect the number of neutrons, the mass number is affected as well because they are related. Remember, we never change the atomic number or the number of protons. Now, in nature, most elements are a mixture of isotopes. So let's say we had a large sample of carbon that we found somewhere. It would be a mixture of carbon with a mass of 12, carbon with a mass of 13, carbon with a mass of 14. The atomic number never changes. It is still carbon, but it does change the mass and therefore the neutrons. So here's an example of very common isotopes. We have oxygen. They all have, I'm going to continue to point this out, 8 protons because it is oxygen. It will always have that same number, but the mass number is what changes here. So we have a 16 mass number, a 17, and an 18. Therefore, that will affect our number of neutrons. Okay? Still oxygen, considered oxygen isotopes. And again, I want to review this. Sometimes students forget this. You will have to memorize where these things are. So again, we have the symbol. We have the atomic number on the bottom, and we have the mass number on the top, and the mass number is protons plus neutrons, or atomic number plus neutrons. Okay? Here is another isotope example, and this is actually what I was referring to, this carbon-14. So you can see here, these are isotopes, because this number is exactly the same, the element is the same, but the mass number is different. So having a different mass number affects the number of neutrons. You're going to hear me say things very often, many, many times if it's important, and this is. So the only thing we're seeing a change in is the mass. The protons don't change. The atomic number doesn't change. So let's go ahead and try an example here. We have a certain isotope, X, containing 23 protons and 28 neutrons. Now, we're trying to identify the element. I find that to be easiest first. First thing we need to do is we can use the protons to get the identity. So I want you guys to make sure you can go ahead and look at a periodic table. I believe I have one on the next slide here. And we need to find something that has 23 protons. So if I zoom in here, I can see 23 right here is vanadium. Now we're going to go ahead and just write the symbol of V. So we have identified the element. And the mass number, remember the mass number is protons plus neutrons. So we're just going to go ahead and add 23 plus 28. Okay, and when we do that, we can go ahead and get our mass number. And we're going to see that that is 51. Okay, so let's go ahead and write our formula here so we know our is 51. So we put our mass on the top and we put our atomic number on the bottom. So we just wrote atomic notation for this isotope. Okay, all right, now I have this periodic table because, again, I knew we'd need to utilize it in this class. If I were you, I'd have a periodic table at the very beginning of your binder. We're going to be utilizing it more than you can even think possible, and I provide you with a bunch as well, and there is one in our classroom. Now, this periodic table is organized in such a way that the periodic table shows elements in order of increasing atomic number. So I want to just point out what this atomic number is, the 1, the 2, and it goes left to right, it increases, okay? And we're going to learn what all these different numbers mean. So again, the whole number is the atomic number, which we know to be the number of protons. And we know this decimal number is its mass number, and we will round that when we need it, okay? We will round it. So I just wanted to point that out. We'll talk a lot more about this later on in this presentation. Now, ions. What the heck is an ion? So we have done neutral atoms, we have done isotopes, now we are on ions. So here's an example of an atom. Okay, we have the mass number, the atomic number, and the symbol. And here is finally what I've kind of been describing to you, an ion. An ion is different. It still has the mass and the atomic number, but it now has a charge. Okay, so what we have here on the top is a charge. So if we see no charge, it is neutral. If we see nothing right there, which we don't, but if we see something here, we're going to call that a charge. I'm going to show you how to utilize that. So when it has this number, we call it an ion. An ion is an atom or a molecule that has gained or lost electrons. So we're talking about electrons here, resulting in a net electrical charge. And remember, again, number of protons is never changed, not affected. These are both still aluminum. They both have an atomic number of 13. If an atom has more electrons, okay, so if it has gained electrons, and it has more electrons than protons, it is called an ion. Therefore, it has a negative charge, and we call that an anion. All right, so let's talk about this. If we have more, so we have protons and we have electrons. Protons are positive, electrons are negative. Let's just say, for example, we have 10 protons. So that is 10 positive charges. If we have more electrons, let's just say we have 12. So therefore, we have 12 negative and 10 positive. What's our overall charge here? 2 negative, right? So therefore, it has a negative overall charge. The atom has an overall charge. When it has a negative overall charge, we call that an anion. We'll talk a lot about this as we go through. Now, if it has less electrons and more protons, let's just flip this. If we had 12 protons and 10 electrons, we'd have more positives. We call a positive ion a cation. Now, I'm going to show you a very dumb way to memorize this, and I have so many dumb little things. Take it as you may. If you draw a little cat here for cation, if you make a little plus sign nose, that helps you remember that cations have a positive charge. Okay, so totally up to you if you want to utilize that. Corny, but I did learn that in high school, and it has helped me over the years. So let's go ahead and reuse and talk about these terms: atom, isotope, and ion. An isotope affects the number of neutrons, and an ion affects the number of electrons. So I just want to continue to reinforce that. So here we have some symbols. We have an atom, and I want to remind you this is the mass, this is the atomic number. Now, does the protons ever change? It's all boron. Does it change? I'm hoping you're yelling at me and saying, no, it never changes. They're all 5s. Okay, they're all boron, they're all number 5. Now, the neutrons do change. Now, when it's written like this format, I love to just kind of use this as a subtraction. So 11 minus 5 gets me 6 neutrons. 12 minus 5 goes ahead and gets me 7 neutrons. And then 11 minus 5 also gets me 6 neutrons. Okay, so the thing that changed was the isotope. That affects the number of neutrons. Now, we're going to go ahead and look at electrons. If it is an atom and there is nothing here, right, nothing's written right there, we know that to be neutral. So therefore, it is the same as the number of protons. This also has nothing here, right? So therefore, same number. Now, this is an ion. We have a positive charge, meaning we have more protons, right? Because protons are positive. Now, if we have more protons, we have 5 protons. And we're going to have more of them. So we're going to actually have 2 electrons. Because when you look at the positive to negative ratio, you're going to have positive 3 more protons than electrons. Okay? We're going to do a lot more practice with that, but give that a little bit of thought. All right, periodic table. There are names for the columns and the rows on the periodic table. The ones you do need to know are these ones. You need to know alkali metals. That is what we're going to call group 1. So that does not include hydrogen. It is lithium through francium. So anything sodium, potassium, rubidium, they are called alkali metals. You do have to know group 2. That is alkaline earth metals. Okay. You do have to know this section. We call this transition metals. You will learn why that name comes about. You do not have to know the ones that I've crossed out. It's just informational. But you do need to know this group right here. We call that group 17. That is the halogens. And you have to know this last group, group 18. And I will tell you where these numbers come from. So you have this one, this one, this one, and this one, and this one. You do need to know. Okay? So if I were to say pick a halogen, you would have to tell me fluorine or chlorine or bromine or iodine, any of those. Okay. Now on the periodic table, we are broken up into 3 categories here. We have the metals. Metals are the most common. They are on the left side. So everything here that is purple is a metal. So most of the periodic table is metal. On the right side here, we have nonmetals. Okay, so nonmetals. Now, I also want to point out hydrogen, which typically belongs right here. Okay, they pulled it out, which I don't love. That is actually, as annoying as this is, a nonmetal. So you will have to remember that that little exception on the left side, let me go ahead and point that out to you right here, is a nonmetal. We'll talk about why it's over there at some point. And then we call this in between, we call these metalloids, and they have properties of both metals and nonmetals. So my trick to help you remember this is if you, we call it the metalloid staircase. If you start your staircase on the outside of boron and make your way down, so just go 1 over, 1 down, 1 over, 1 down. And everything that touches this staircase is a metalloid except aluminum. Okay, so boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astenine. So all of these touch the ladder. We call this the metalloid ladder. I'm going to go ahead and reinforce this. So drawing this is important. The only thing that touches this that is not a metalloid is aluminum. So think of aluminum foil. We know that to definitely be a metal. All right, we're continuing on with just basic information of the periodic table. We are going to talk about groups. Groups are columns. They are up and down. They are vertical. There are 18 groups. 1, 2, 3, 4, all the way through 12 here. We're going to continue 13, 14, 15, 16, 17, 18. And remember, we talked about their special names. Group 1, alkaline metals. Group 2, alkaline earth metals. We did 3 through 12, transition metals, 17 halogens, 18 noble gases. So we call those groups, okay? Periods are horizontal. And let me give you a memory trick. Periods are at the end of a sentence. Sentences are horizontal. You write sentences horizontal. So just a nice little trick. So let's go ahead and write the period numbers. Number 1 is hydrogen, and it goes across to helium as well. 2 is lithium, beryllium, all the way over to boron and carbon, so it goes all the way across. 3, 4, 5, 6, 7. Now, you're saying to yourself, why are we not referring to these last 2 groups? Well, these groups actually come out of this section. So 57 to 71 actually belong in here. The issue is, it kind of makes the periodic table too long, and it's hard to fit on paper. So we pulled out radioactive elements so that they're an easy reference. Hey, that's radioactive. And because they have a couple different properties we're going to learn. So this 57 through 71 belongs there, and then this 89 through 103 belongs here. So you have to imagine them popping out. So this 57 through 71 is actually still group 6 because it's here, and this 89 through 103 is actually group 7 as well. Okay, so we do not have 8 and 9. We stop at 7. So just a couple properties of metals. Remember, metals make up most of this over here, including this. Metals are typically solids. So for example, think of iron, think of lead, think of aluminum. They're always solids. They have high melting points. They take a lot of heat to melt. They have metallic luster, and this is a term you're going to want to know. Luster means shiny. So if you think about aluminum foil, it has high luster. They are good conductors of heat and electricity. We use copper and things like that in construction because we are, making sure things are conducting throughout the house. And then we have 2 more terms here. We have ductile and malleable. Ductile means it can be formed into thin wires. So for example, copper wires is very ductile. And malleable means it can be hammered into sheets. So for example, think of aluminum foil. All right. So some good properties of metals. Now, we utilize metals for so many of their properties, specifically their ductile and malleability, and also their high melting point. So that is why they're majorly used in weapons and construction and, tons and tons of stuff. Now, nonmetals are basically the opposite. They're typically gases. They have low melting points. It doesn't take very much to evaporate them. They are very dull. They really don't conduct electricity or heat, and they are very brittle. We do not use these in everyday building. You can see the nonmetals are over here, and mostly they are oxygen, which we breathe, chlorine gas, bromine, iodine, which is used in the medical field, fluorine, those things, helium for balloons. You can see most of those are gases. Okay? All right, so we are going to continue on. We're almost done here. Thanks for sticking with me. I told you that solids are usually, most of the elements in the periodic table are solids because most of them are metals. There's only 2 at room temperature. Room temperature is about 70 degrees Fahrenheit, 25 degrees Celsius. Bromine and mercury. Mercury is Hg, so bromine is Br. So those are the only 2 liquids at room temperature. And then gases is group 18. We call that the noble gases, and hydrogen, oxygen, nitrogen, chlorine, and fluorine. Okay? You don't have to memorize those. just knowing most things are solids are important. All right, now I'm going to truly introduce you to the term ionic and molecular. We're going to be using the heck out of these, so just stick with me here. Ionic means we have a metal and a non-metal. Remember, on the periodic table, we're made up of metals over here in the green. Oh, excuse me, I should use green here. And we have non-metals on the right side. So when we have an ionic compound, it's an element from the left side joining with an element from the right side. And what happens here is we see a transfer of electrons, and we create what we call an ionic bond. We're going to talk a lot about that. So the metal and the non-metal transfer electrons, and they become a cation and an anion. Remember, a cation is a positive ion. Remember our little cat face here? And an anion is a negative ion. So, for example, NaCl, which is typical table salt, is a metal and a non-metal joining together. We have K2S. K is potassium, and that's an S. I always make my S's look like fives. So potassium sulfide is another example. That is a metal and a non-metal. Okay, so just understanding metal, non-metal, transfer of electrons. We'll talk more about that later on. Now, molecular compounds are oftentimes called covalent. I have always referred to them as covalent, but books are more recently referring to them as molecular. So if you watch a video somewhere else, I want you to be comfortable hearing that term. We use molecular and covalent pretty interchangeably. And a molecular compound is just two nonmetals, and we share electrons. So sharing is the big thing here. Transferring is that big one there, two nonmetals. So for example, we could have SO3 like we talked about before. We could have H. So I want to remind you, H, even though it is on the left side, is considered a nonmetal, HBr. So two nonmetals. We do not have any bonds that are a metal and a metal. Okay, metals by themselves make what we call metallic bonds, and we may talk about that in this course. But big one we're talking about is ionic and molecular or covalent. Now we're going to talk a little bit about charge prediction here. Again, we're going to get really deep into this, so just stick with me here. The periodic table tells you so much, and everything can be figured out charge-wise by the group that it is in. I'm going to continue to use that word group. Groups are vertical. So everything in this first group makes what we call a +1 ion charge. So when it decides it's going to bond, okay, let's say it's happy by itself, but it decides, hey, I want a partner. I want to be more stable in the environment. I want to bond. If I want to bond, I'm going to make a charge. I'm going to have to form a charge, excuse me. So if it is any of these, it makes a +1 charge. Now remember, +1 means there are more protons, because it's positive, than electrons. So really, when we see a +1 charge, that means that we have lost an electron, lost one electron. Now, beryllium, group 2, beryllium, magnesium, calcium, when it decides it's going to join with a friend, okay, when it makes an ionic bond, it is going to make a +2 charge, meaning it's going to lose 2 electrons. Now, I promise I'm going to talk more about where these numbers come from, why. In this chapter, they just give you a little bit of an introduction. I don't love this order, but I know that I will get you there as we move along here, okay? So things over here, metals over on this left side tend to lose electrons. And then on this right side, they are nonmetals, they gain. So everything over here on this right side, when they have a negative charge, they mean they are gaining electrons. So if I were to ask you what charge does nitrogen make, you would say it makes a -3 charge, okay? And we will be using these a ton, so if you're like, oh, I'm a little bit confused, that's okay, all right? All right, so if I were to say what charge does the alkali metal group make, you would know that alkali metal group is group 1. If you were to look in group 1, you would see that it is a +1 charge. If I were to say what charge do the halogens make, you would know halogens are group 17. Group 17 are shown here, and so they make a -1 charge. Now, why are we not seeing this last group? These are the noble gases. They do not react with anything. They do not form bonds, so they have no charge. So that is why on this picture they're not showing them. So that is group 18 right there. So just a little bit of practice. And that actually finishes us off with this chapter. Things that you may see in the textbook that I'm not covering will not be included on any test. I'm really just showing you the basics here, picking out the important information, and we will do more